welcome to Module 40 on baselines and leakage traps. By the end of this module, you ought to be able to define and justify baseline models for classification and regression tasks. You ought to be able to compare a baseline to a more complex machine learning model using appropriate metrics. You'll be able to explain what data leakage is, identify common leakage patterns in code. You'll be able to refactor simple machine learning workflows, including with something called k-fold cross-validation. And you'll be able to diagnose suspiciously high performance and propose sanity checks and safer alternatives. So in practical data science, which is important for this course, there are a variety of ways that your modeling can fail and fail pretty badly. But we have to start with some naive, like early types of failure modes. The first one is just not having a decent baseline. Not absolutely every situation calls for having a baseline, but the vast majority of them do. A baseline is basically just a pre-existing model, sometimes very simple, but not too simple, against which you can compare the model that you're thinking of deploying or developing or otherwise is your kind of preferred model. So imagine you build a fancy model. Imagine you're now in year 3 of your studies and you're getting familiar with deep neural networks and you've added some tweak to it and you think theoretically this tweak ought to make this model a lot better than the previous alternatives. Imagine for a moment that despite all of the effort you put into this fancy new model, it's only marginally better, or maybe it's even a little bit worse than some ridiculously simple baselines. Here I have two of the most naive baselines possible. If you're doing classification, you can have a couple of different categories to which a particular data point can belong. And as we talked about last time, classification is just choosing from among these possible types, categories, labels, classes, however you want to call it. Imagine there's some incongruity in terms of the proportions of how often each of these categories appear in your data, in your training data, and whichever one is the most frequent. I shouldn't say majority, because if you have like many classes, if you have 100,000 classes, it's very unlikely that any one of them will occur 50% plus one of the time or more. So whichever class is the most frequent, which is called the plurality, if you always predict that one, that's a really simple baseline that you'd expect to have some kind of like minimal level of performance. Otherwise, predicting the historical average, if you're doing regression, again, you're trying to predict something on a continuum. You just predict whatever the average is previously. That ought to give you something that's like a minimal level of reasonableness. Now imagine like those dirt simple baselines, basically picking randomly essentially with almost no knowledge of how the data actually interact with the label or the class. Your fancy new model doesn't do any better than those. That would be pretty embarrassing. And so imagine if you don't even do that comparison. You'll never know how bad it is because you didn't actually compare your fancy new model with anything. So the result is you've wasted all this time. You've wasted all of the complexity, all of the work that it takes to train this model. And you might kind of lean into some of the esoteric, interesting aspects of the model. And that would give the guise of progress, but really it's nothing of the sort. That's a first failure mode. You just didn't compare enough. So no baseline is like an extreme case of a phenomenon in which whoever's putting out these models just didn't do enough training more generally, or more comparisons, more experiments. Another kind of failure mode is that there's some kind of leakage happening. So leakage is kind of a generic term that we're using kind of broadly at the moment. It means leakage of information, so more or less in the information theoretical sense. So it's not exactly like something that you can have units on or something that you can necessarily count. Now that I'm saying it, I mean like there are units in information theory and you can count information in information theory. That's almost exactly the point. But I guess what I'm trying to say is that information in information theory is usually something a little bit more esoteric than something at the surface. But the information can flow and can spill over in your experiments in all kinds of different ways, which is problematic. So in this scenario, you have a model that has 95% accuracy or some other metric that sounds impressive on some test data. And remember, imagine even you did the right thing and you kept the test data sacred and you didn't touch it until the last moment. And so 95% accuracy on this data that you've never used seems impressive. So whoever the stakeholders are, this could be your employers, your colleagues, venture capitalists if you're trying to pitch your model in an entrepreneurial venture. They're thrilled. Maybe you get your paper accepted, maybe your dashboard that you developed for your company is shipped, et cetera, et cetera. But eventually, like it could be months later, in practice it could be weeks or days later, this model is deployed on data that it's truly never seen before, and performance just collapses entirely. And we'll get to some deeper specifics here, but the root cause can be just that your model was evaluated relatively sloppily, and information that was kind of in the test set, maybe not directly, but maybe indirectly, leaked into your training, and so your model ended up kind of peeking at the answers of a test and getting performance that was like overly inflated. So the main messages here in this slide, which I wanted to spend a bit of extra time on, was that good machine learning does not mean that you just get high accuracy on some split of data, like a test split, even if you're apparently very careful. At the very least, you need to be able to beat a strong baseline, much stronger than these, without cheating, either explicitly or implicitly. So again, just to define it again, a baseline is a simple, transparent prediction rule, or a relatively simple model that sets the minimum performance that any serious model must beat. Right? Whatever you're developing, it should be better than this. Often, in cutting-edge machine learning, our baseline is often something that appears to be the state of the art. Maybe a few months ago, some group released a model for a particular task, and they achieved some performance that appeared to be the best in the world, and that's a very good baseline to try to beat, right? Like, as opposed to randomly guessing or something like that. So baseline, there's a wide range in what constitutes a baseline. It can be something extraordinarily simple, which is not great. It's a bit of a straw man. And it can be something extraordinarily difficult to beat, which is far more impressive if you happen to overcome it. So these are some simple baselines again. And again, these are kind of bad ones. For classification, majority class classification. Again, this should maybe be called plurality class classification, but it's not. Always predict the most frequent label. You're going to be you're going to be more correct than if you selected like a very rare label. But still not necessarily the greatest. Stratified random means basically sampling the labels according to the observed class proportions. So maybe like one label turns up 95% of the time, the other one 5% of the time. Don't just constantly predict the first class, the former, predict the latter with like 5% probability. That might be a little bit more realistic. It won't fall into pathological problems, which we'll talk about in a moment, but still not a great baseline. But if you're not beating these, then you're having a bad time. Regression, like we talked about before, just predict the training set mean, completely uniformly. It's pretty boring. The median baseline, predict the training set median if that's available to you. Again, that would be a constant prediction, and it comes with its share of problems. The naive time series is that tomorrow will equal today. And this is fine, but not great. So things we like easy to explain to non-technical stakeholders. We like robust to overfitting, and we like models that provide sanity checks. Data leakage is any situation where your model gets information during training that could not be available at prediction time in the real world. And so these include things like train test contamination. We'll see this in a moment also, an example of this, but imagine you're computing some statistics like the mean, you're scaling the data, and you do that on the entire data set, and then you do the split afterwards. So imagine you're doing the super simple baseline of always predicting the mean or the median on your test or evaluation sets. This is not great, obviously, if the mean is computed with some information from the test set. Okay, so technically it might not look like the end of the world, like all you have is a mean, and the mean will be shifted a little bit up or down. based on whatever the data are in your test set. You're not actually using the test data to make your prediction, so what's the big deal? But like it's still information that's leaking a little bit into the model, and if the test data is a little bit higher than average than the training data, then that'll shift the mean upwards a little bit and result in models that have overinflated performance, right? Like you're still technically cheating, even if it seems pretty innocuous. So that's kind of the most obvious thing, and we'll see an example of this. Somewhat a little bit more maybe nuanced is, imagine if you have a ton of data and you have a lot of data points, and you do the careful thing, and you very quickly, early in your code, split the data into training and test, and then you keep the test data totally separate, and you do all of your operations on like training, maybe on a little bit of the validation data to tweak your hyperparameters. But what if you have like the same source of all of these data points producing data that occurs both in the training set and in the test set? So I'll give you an example from my own experience. We had a lot of data from patients, and we had samples of their speech. We had a lot of files of their speech, and we split the files into like training and test with approximately 80-20 split. And then you take the training data and you keep the test data separate like you're supposed to, and you train a model on just the speech data that occurs in the training set. The challenge is these especially these highly performant, highly capacious, like deep neural networks can learn an awful lot. They can learn not just kind of what they're meant to learn, but also any other information that they, so to speak, think would help them with their task. And for us, that happened to seem to learn the identity of the speaker. So if there's 7 or 8 examples of the same speaker's data in the training set, the model would, just like a human, would kind of like learn to recognize that speaker. Right? This is speaking very loosely, and I'm anthropomorphizing the machine learning model, obviously, but it's as if the model was saying, oh, I recognize this person's voice. I remember in other training examples, this person was diagnosed with this disease, so therefore it's going to help me diagnose them with the disease going forward. It's not exactly that straightforward, but that's the gist of it. So then the test set comes along. We have new samples that we've absolutely never seen before, but the model has learned the voice of that person. And then the model says, well, I already heard this person's voice in the training set. And in the training set they had the disease, so I'm just going to classify them with the same disease that I saw them with before. And hopefully you can see how that's a form of cheating, right? In real life, when you're doing diagnosis, you don't necessarily have the diagnosis beforehand. You want to be able to generalize the situations where a new patient comes in that you've never seen before, and you don't want to kind of have this kind of shortcut that's occurring. So discovering this, we ended up doing some kind of a form of stratification where the training set, we stratified by the source, by the individual or the speaker. So all of that person's data was in one set or the other, the training set or the test set, but not both. And the net result was when you get the test set, all the speakers, all the sources of the data were new, right? And that kind of solved that problem of having kind of pre-existing knowledge of individuals that produce data in the test set. Hopefully that's clear, but that was kind of a pernicious problem that I think a lot of research in machine learning, kind of takes for granted. Obviously, like you might not be doing diagnosis of disease and you might not be dealing with speech data, but the principle generalizes. So there's still more problems. So target leakage, this is where features that are direct or near direct functions of the label occur in both the input data, or what we called X before, and the thing we're trying to predict, which is Y. So imagine what you're trying to predict with a model is whether or not a particular client of your bank will default this month. So this is the target. And then imagine if you have another variable that says this person has defaulted last month. Okay, so these are technically 2 different variables, and they're measuring 2 different things, but those 2 values are extremely correlated with one another. And indeed, if you know that the person has defaulted last month, then the chances of them defaulting this month will increase dramatically, right? So it's kind of 2 variables which are highly correlated in both the input X and the output Y. This is like information that you might not necessarily have, right? Whether or not they've defaulted last month. Similarly, if you're trying to like look at a patient and see if they're going to be readmitted or not, like you want to, like if a patient is in your hospital, you want to discharge them and send them home, but you want to ask before you do that, like if I send them home, is it likely that I'm going to have to readmit them in the future? Because readmitting them, it means like worse outcomes for the patient, greater costs for the hospital, et cetera, et cetera. But imagine you also have a variable in your data set that just says hours to readmission. Obviously, there's going to be a shortcut between how many hours exist between now and readmission. That will basically answer this question for you without having to learn anything else, right? So this is another shortcut. You would not have information about what happens in the future if you're making a decision now. So hopefully that's also clear. I mean, to a large extent, this is pretty much the exact same problem as temporal leakage. I mean, here I'm trying to make the point that variables and input and output can be too highly correlated with one another, and you won't necessarily in real deployments have access to that particular input variable. But similarly, this example can apply here to temporal leakage. If you don't know, if you want to predict whether or not a customer is going to churn at day 0 currently, but you have access to information about what purchases are going to be making in the next 30 days, given a particular timestamp that you've already recorded in your training set. This is like you don't have information about the future. Most of us don't. Some people claim to, and they're obviously bogus, right? So don't assume that you're one of these clairvoyant type people. So leakage, like all of these different kinds of leakage types will give the model extra information during training, and when you evaluate it during the whatever test set you have, it'll make your models look unrealistically good. And I call them notebooks, assuming you're doing this in the Jupyter notebook, but in any kind of evaluation, really. And you're going to have too much confidence in your deployment, and then when you actually do go ahead and deploy it, it's going to fail miserably, right? I think I've mentioned this before, and I'll probably mention it again, but it's far better to claim a model has like 86% accuracy, so to speak, and then when you deploy it, it gets between 84 and 87% accuracy, than claiming a model gets 99% accuracy, and in deployment it gets between 84 and 87% accuracy. A robust model beats a model that one time occurred, one time behaved nicely. So here's kind of a clean evaluation workflow and a leaky one, just to hammer this home with visuals. The top is kind of the correct pipeline that we'd like to have. We start with the raw data. We immediately split into our train, validation, and test sets, which we talked about in the previous module. Any kind of pre-processing, which includes scaling and noise correction, filling empty values, and so on, all the different steps we took previously. That is done on the training set only. Whatever, like, to do that, sometimes you need to learn a model, like you need to learn what the means and variances are in order to do Z-score normalization. So figuring out the mean and variance you obtain from the training set only. But then you can apply that particular value on the test set later, so you can still shift over all of the test data, but using the mean and the standard deviation that you obtained on the training set. So you can basically shift the test set into the space defined by the training set. And then you train the model only on the train, and then you evaluate on the validation and test. There's the part here in the middle is where you pre-process the validation and test set also. That's kind of implicit right here, but that's important to not forget. The leaky workflow obviously starts with the raw data also, but then the pre-processing happens on everything, right? So you take all of the data, you find the means and the variances for all of your data to do the Z-score normalization of the data. Then you split the training and test. Then you do the pre-processing for your training model and the test model based on the mu's and sigmas you obtained on all of the data. And then what that gives you is, again, mu's and sigmas, which have information in them, so to speak, from the test set that sets the scaling of your training model in a way that's advantageous for the test set, and then your scores are overly optimistic and therefore bad. I want to basically take a brief detour to talk about why single train sets and test sets is fragile, and why you have to maybe avoid these also. So, a single split is like one random way to carve up the data. We had all of our data set, and then we shuffled, we permuted all the indices, and then we chopped off 80% and kept it for training and the rest for test. That's better than training and testing on the same data set, obviously. But, if you just happened to have shuffled things in a slightly different way and then separated into 80% and 20% respectively, then you would have had like a different test set, and the test sets you obtain could have varying degrees of easiness or hardness with regards to evaluation. You might have ended up with particular data points that are hard to classify or do regression on, or an easy set. So the performance you would report on the test set might be lower than you'd expect it to be. It might be higher than you'd expect it to be if you just had happened to sample more test sets or a different test set. This goes back to one of the previous modules on bootstrapping, and we had these distributions that we were generating by taking many samples of the data and computing means for all of these different samples. You had a distribution that showed like a lot of variability. So what would happen if you happened to take a test set that had a data distribution that was very hard or very easy, right? So the performance you're reporting, as if it's the gold standard, this is the true performance of the model on a deployment set, is just one possibility. And especially if you have a small amount of data, which can be the case if you're dealing with like unique deployments, like you had a very particular like specific use case for which there's no other data that exists. You might have a small amount of data, and it can exacerbate this problem. So here's a little demo I wanted to show of, again, a very small data set that shows different kinds of splits of training and test, and how this can affect your performance. So here's just a few splits. So there's 6 splits. This graph shows 2 classes. In blue is class 0, and in red is class 1. And you can kind of imagine there's like a border between these, splitting the data. So blue's on the left, class 0's on the left, and class 1 is on the right. And you train a model to learn what that boundary is, and then you can do classification. I've highlighted, here there's like arbitrarily there's the circular points represent points that are easy to classify. They're far away from this boundary. And then near this boundary are these diamond-shaped or rhombus-shaped data points. And these represent hard points to classify. They're really close to the boundary, and it's not exactly clear to a model if like this square over here should be classified as a square or as classified as red or blue, class 1 or class 0. So close to the boundary, it's hard to tell to which class this should belong. Hopefully that makes sense. Now, the bigness or the smallness of these data points represent whether I've included them in my test set or my training set, respectively. So here, all these big data points represent my test set. Okay, and here, these big circles also represent examples in my test set. So I just happen to randomly sample these points, and you can play what I want with this, like these different settings down here for my splits. You can see how some dots become big or small. Like the big dots always represent the dots that are in my test set. Along here at the bottom also, we compute the validation accuracy. So if we were to perform a classification here and to see how accurate our model is, just based on the same exact data, and not moving anything else around, and just happening to sample different subsets of the overall data set for testing, you can get anywhere from let's say 82, 83, 80, 83, 79, 81. So you get a spread of about 4% in performance just by sampling different subsets of this data for testing. So 4% is actually, like in many machine learning applications, a huge amount. Like often the difference between a strong baseline and the new state of the art is sometimes on the order of like 0.5% or some smaller fraction of a percent in difference. There's a whole lot I could say about whether that's meaningful or not, but regardless, 4% is huge, both in terms of just empirical results, but also, even 0.5% can mean a great difference in terms of deployment if it means, you're like if you're scaling up to hundreds of thousands or millions of data points or customers, that can indeed have like tens of thousands or hundreds of thousands of samples classified one way or the other, right? So that scales up to being a big deal. And all of this this 4% difference is based on nothing more than a random sample from the data set used for testing, right? So hopefully that gets the point across that like a single test set and claiming, oh, this model gets 79% accuracy is insufficient. So our idea is to reuse the data in a more systematic way. We want an evaluation procedure that will at some point use every example for training, at least most of the time. Every example will be used for testing at least once. So if there's some kind of particular outliers or weird data points that behave atypically, like we will see it, we will see it in operation in deployment at least once. And this whole process will be systematic and repeatable, not like ad hoc or totally random. Like we'll be able to reproduce results in a systematic way, so others can get the same results as us. Again, like if we happen to split something, we report 79%, or we're worse yet, we split it this way, we report 83%. Someone else takes our code and our data, gets another random split and gets 79%. They'd be pretty angry at us for overinflating our results. And we don't want that. We want something that's repeatable. This is the idea behind k-fold cross-validation. In k-fold cross-validation, we will split all of the data into k-equal folds or partitions of almost exactly the equal size. There are some variations here, but just to keep things simple, we basically partition everything into 5 equally sized silos or partitions or folds. We take one of the folds, one by one in turn, and then we treat that fold as the validation set. We take all of the other k-1 folds and we combine them all together. And then we train the model on those k-1 remaining folds. Once that's done, we test on our held out fold. We get our metrics, accuracy or whatever it is we want, the mean squared error, the mean absolute error. And then we record that metric and then we put that fold back, the one we held out, take the next fold, and then repeat the process, k-1 more times. So conceptually, what we do is we shuffle the data first. This is optional, but it's common. We can split into k-folds, and then this is what I just said. So this is this visualization over here represents the 5 folds. Like I've chosen k to be equal to 5, and often k is equal to 5 based on precedence. Like I think I've mentioned before, precedence is like a lousy way to make your decisions in science. Like if you had all the time in the world, we'd do experiments to evaluate which value of k is optimum, but usually people just set k to be like a typical number, like 5, and then off they go. And then this represents the process I mentioned. So here are my 5 folds, the 5 partitions of the data. I'm going to take the first fold, hold it out, train a model on the combination of the 4 other folds. I could combine them into one big data set. I'm not going to train 4 different models. I train one model on these 4 combined, evaluate that model on fold 1. That gets me a metric 1. And then I return fold 1 to the group and then proceed to hold out fold 2. I combine folds 1, 3, 4, and 5 into one new training set, train a new model from scratch, evaluate that new model once I'm finished on fold 2, which is held out from this run. Get a new metric, store that somewhere, and continue. Okay, so hopefully this makes sense. Maybe some of you might be getting confused. You might be like, wait a second, didn't I see fold 2 previously when I was doing training in run 1? Isn't this exactly what I warned you against? Don't evaluate on data you've previously trained on. And that would be a reasonable response, and that would be good that you remembered that advice. But you have to remember here that we're doing all of these experiments in isolation, and by the time we get to run 2, we're going to be training a whole new model from scratch entirely. We'll start with entirely random parameters. We can literally delete or shred the previous model. Actually, we wouldn't do that in real life because we might want to go back to it and retest it. But the point is, whatever model is going to be used to test on fold 2 is a completely different model than the one that was used to test in run 1. I think I'll mention this in a while, but just quickly, like if I do 5-fold cross-validation here and I get 5 metrics, 1 for each run, then I can also compute things like the mean of these metrics and the standard deviation of these metrics. So if, again, returning to this example, if I had done 6-fold cross-validation and these were my 6 random splits, I'm not sure if that actually makes sense here, if these tests are actually, no, I guess they wouldn't be, because I can see a couple of data points being used several times. But anyway, here there's a certain variability, like there's a variance and there's a mean in terms of these validation accuracies. I'd be able to store that, and I'd be able to see, well, sometimes I can get as high as this metric or as good as this metric. Sometimes I get as badly as that metric. On average, this is the metric I'd expect. That's a bit more reasonable and explains the behavior of a model being deployed in general. Some worked examples. We'll start with classification. Let's simulate a simple loan default prediction task. So our feature is going to be a numeric risk score summarizing a customer's past payment history. The label we're trying to predict is whether the customer defaults next month. So it's just we have a binary classification task. Either it's class 0 defaulted or class 1 not defaulted. And then we'll compare a couple of baselines back to the original topic of this module. A majority class baseline is just like, well, whichever one of these two categories occurred most frequently in my training set, always predict that label no matter what. And then we're going to train a KNN classifier. KNN classification is literally the topic of the very next module, so for now you can treat it as a black box classifier. This is really like another baseline classifier that's incredibly simple. It's barely more advanced than a majority class baseline, but here this is going to be the empirical model that we're going to be comparing. So here's all of our code. We're going to be doing more with sklearn than maybe we have before. We have the train test split function, which we saw previously in the previous module. We have a couple of classifiers. So sklearn neighbors is a collection of classes that implement neighbor-based classification and other types of modeling. Kneighbors classifier is our KNN classifier. Dummy classifier is going to be our majority class classifier. We're going to be measuring accuracy, and we're going to be displaying confusion matrices in a moment. And then everything else is pretty much as typical. Here we're just going to synthesize the data. So the risk score is a normal distribution. We talked a lot about that in previous modules. The true probability of defaulting will just be like this is just a random score for the purposes of this example. There's a little bit of a bias over here, 0.1. There's a scalar here applied to the risk score. This is going to be the probability of defaulting. We clip it. And then this probability will be put into a binomial distribution to have these two outcomes, whether they defaulted or not. And we have the risk score and the class in a data frame. The risk score is our X, our inputs. Whether they defaulted or not is our Y, our outputs. We split all of the X's and Y's into training and test, like we talked about previously. This is 30% held out for testing, and we stratify based on defaulted. So the class should be more or less balanced between the training set and the test set. Like the proportions should be roughly the same across those sets. Here we call our classifiers. What kind of dummy classifier are we using? Well, we're going to be using the most frequent label to classify. And then just like everything else in sklearn, not everything else, but most models have this fit function, which we can run on our training data. This kind of tweaks the model. Once this model is tweaked and the parameters are set, we can make predictions on our test set. This gives us our predictions. And then we can compare our predictions here in Y-dummy to the true values of what we should have predicted Y-test. This will give us an accuracy score, and we're going to store that in dummy. And we basically do the same thing for k-nearest neighbors. We fit, we predict, we get our accuracy on our predictions. And then here we're just going to be reporting them. So, here the accuracies are ridiculously close. They're literally exactly the same. The majority classification gets 53.9% accuracy. K-nearest neighbors gets 53.9% accuracy. Sometimes I like going into these examples and then tweaking things so that like the model that's supposed to be more impressive, even something as silly as KNN, gets more impressive results to avoid this pedagogical problem of results being exactly the same. But I kept this in for this reason. Like right now on its surface, looking at these two numbers, it would look like, oh, this baseline and the k-nearest neighbors are equivalent to one another. They both get exactly the same performance, which would suggest to a naive person that you are increasingly not, that these models are essentially equivalent. And I think for most people out there in the world, that would be the conclusion that they would draw. But you know better. You know, for example, you know something about how at least the baseline model is choosing its classes. You know that it's always going to choose the majority class. So here, this is the confusion matrix. The predicted label is on the horizontal axis, the true label on the vertical axis. And the counts here basically represent the number of times, something that was actually class 0 was classified as predicted as being class 0. Here, there's a small amount of an advantage, like there's 97 examples of class 0 in our data, there's 83 examples of class 1. So because class 0 is the majority, this model will always predict class 0. And you can see that happening in this confusion matrix. The predicted labels are going to be always 0, so 97 times, sorry, it's not 97 examples. Yeah, it is, sorry, it is 97 examples of the true label here. So out of all damn it. So here we're going to simulate a lone default prediction task. Our feature is a numerical risk score that summarizes a customer's past payment history, and our label, the thing we're trying to predict, is going to be just whether or not the customer will default next month. So there's two classes, defaulted or not defaulted. We're going to compare two classifiers. We're going to go back to the idea of our majority class baseline, which I previously said is kind of a ridiculously simple baseline, but it'll raise a particularly important thing to mention in a moment. And we'll compare this against a k nearest neighbors classifier. So KNN, or the k nearest neighbors classifier, is going to be the major topic of the very next module. So we're getting ahead of ourselves a little bit, but we needed some module here, some classifier here to compare. So for now, just treat KNN as like a black box classifier that you don't necessarily know how it works yet. But it classifies, given input, it makes a prediction for a label. So I'm going to look at the code quickly. So we've already seen model selection in the previous module. This just takes our data and splits it into train and test sets. We have in sklearn, there's a category of classes called neighbors. These are a bunch of neighbor-based classification, regression, clustering algorithms. And from it, we choose k neighbors classifier, which is the name they give to the KNN classifier. We're going to have a dummy classifier. This is like a dirt simple baseline, and it can take a couple of different forms, and we'll set it appropriately in a moment. And then to do evaluation, we'll have a few metrics. We'll just compute accuracy scores, and then we'll demonstrate a confusion matrix afterwards. So as always, for reproducibility, we set our random number generator so that we can be reproducible. You can do experiments on this again, like changing the random number generator, its seed. We'll give you slightly different results every time, and it's up to you to maybe do some experiments on that. We're going to take 600 examples in total, and we're going to generate synthetic data. So this data, the risk score, is going to be drawn from a normal distribution. That risk score will then tell us what the probability of defaulting will be. We have this very simple model that we construct, just synthetically for the purposes of this example. There's a little bias of 0.1. There's a little scale of 0.007, and then that'll be multiplied by our risk score. This will be probability that is then clipped to these parameters. And then we're going to put in like an overall binomial distribution of default or not default, which will be a binomial distribution, which again has two possible outcomes whose probabilities are inverses of each other. So for all of our risk scores, all of our risk scores are going to be associated with a probability of defaulting, which will be transformed into this class, defaulted or not. And so we have all of our data in our data frame. We didn't necessarily need this data frame. Like I almost immediately pull out the input to their model, our risk score, and store that in variable big X. And I'll take our defaulted column, which is our class we're trying to predict, put that in lower Y. We use train test split to split the data into 70% training, 30% testing. We stratify on the label, Y, so the proportions of default and non-default are going to be roughly equivalent in the train set and the test set. Then we have our classifiers. We have our silly baseline, our dummy baseline. What kind of dummy classifier do we use? Well, we take the strategy of just classifying the most frequent one. You can look up the documentation for a dummy classifier if you wish. There's a couple of other strategies you can use, and most frequent is the one we're looking for. I think almost all classifiers in sklearn implement a fit function. The way they fit their parameters are going to be different for everyone. For the dummy classifier, it just looks at the prior probabilities of the labels, and then it'll decide to always predict that label. Nothing fancy. Other models, set their internal settings, their parameters in different ways, but fitting is always done on the training set. And then once you have that model, then you can take the test set and you can make predictions on what y should be in the test data given just the inputs x. And then you can compare your predictions, y dummy, against what they should have been, y test, and that'll be passed through this function accuracy score, producing our scores. K nearest neighbors, we'll talk about this again in the next module. It takes us, one of these parameters you can pass to it is the number of neighbors. This will make sense next time. I'm setting this to 15. Again, K nearest neighbors being a classification model in sklearn implements the fit function. So we fit this model on the training data given x's and y's. Once that model has been trained, we can make predictions on the test set given only the inputs. The y's are the things we predict, so y underscore KNN are the values we predict. We can compare those predictions against what they should have been using the accuracy score function and store the accuracy in ACK KNN, and then we can just look at ACK dummy and ACK KNN. So far, so good. Now, here we have the situation in which our super simple majority class baseline gets 53.9% accuracy, and our barely more complicated KNN model also gets 53.9% accuracy. Occasionally, when I encounter this situation when I'm producing the slides, I'm inclined to maybe tweak things a little bit in order to show progress to you, to show you that we can produce models that are better than the baseline. But I kept it like this for two reasons. The first one of which is just to reemphasize this issue that not every experiment you're going to get is going to give you fantastic results, to normalize failed results, because despite what you see in the news or read in academic papers, failure is common, and you have to learn to overcome it. I also wanted to show you this exact same performance to illustrate the fact that just because these two models get the same performance, it doesn't mean that they're actually equivalent to one another. I think a lot of people out in the world would see that these two models get the same performance on a test set and would therefore conclude that these models are absolutely equivalent to one another. And that's a naive notion that you, being increasingly expert in data science and machine learning, have kind of intuitively learned to understand is not the case. You know already that a baseline majority class, a majority class classifier baseline, will always predict the same label no matter what. And we observe that in this confusion matrix over here. So here, this confusion matrix basically compares the number of times there's a certain combination of a predicted label for a true the label it should have provided. So in here, for example, out of the out of the test set data, there's 97 instances of class 0, and all 97 of them were classified as being class 0. There were 83 examples of class 1 in the test set, and all 83 of them were classified as being class 0 also. In fact, this majority class classifier, because it always predicts whatever the majority class was, is going to predict class 0, and there's 0 instances of it predicting class 1 in this test set. I don't know exactly what the proportion was between class 0 and class 1 in the training set, but if it's roughly the same order of magnitude, you can see that 97 to 83 is relatively close to one another. There's not that much of a difference, between these proportions, but because the majority class classifier always has to predict whatever the most common class was, it's always going to predict class 0 no matter what, okay? The KNN, again, we'll talk about this next time, has a more diffuse confusion matrix. There are 60 instances of class 0 that are correctly classified as class 0, and there's 37 instances of class 0 which are mistakenly classified as class 1. For a confusion matrix, we usually want the big numbers to occur on the diagonal. We want class 0 to be classified as class 0. We want class 1 to be classified as class 1. And any numbers off of the diagonal represent misclassifications. So there's 46 examples in the test set of class 1 being mistakenly classified as class 0. Okay? So, somewhat coincidentally, these two models, which behave in different ways, ended up with the same exact accuracy, but their performance is very different, right? You'd expect, at least some of the time, if you had instances of class 1 in a test set or in a deployment, at least some of the time class 1 would be classified as class 1 in a KNN classifier, but it's never going to be the case in the baseline. Okay, I think you know intuitively now that this is a problem. This is obviously a form of discrimination against class 1, but it results in a classifier that is essentially not very informed by its sensors, by its inputs, and it's going to be problematic in other ways. So this 53.9% is not equivalent in meaningful ways to this 53.9%. So some questions to ask yourself. I'd advise you to just jot these notes down. I want you to ask, this is going to be obvious, but does the KNN beat the baseline by a meaningful margin or not? And if not, is it because of the feature being weak? Is the model misspecified? This is a question maybe you can only answer once you come back to this module for studying after you've seen the next module. But just try to play around with the small amount of code I've given you and see if you can make any tweaks in order to get any kind of different results than the one I just showed you before. And then try to learn, time permitting, or try to get a sense of what levers you can pull in order to get different performance. So what kinds of mistakes does each model make? You know something about the baseline. The baseline always gets the majority class right, but it obviously misses all of the minority classes. But what kind of mistakes does the KNN make? It does a little bit better on the minority cases. It does better on class 1 from the previous example. But why is it making more mistakes on the majority class now? So again, look at the data, visualize it using the techniques we saw previously. Play around with the numbers you saw previously, even adjust the model itself if you want, and see what you come up with. Maybe sample things differently. Instead of taking 30%, take 10% or 20% for testing. So there you go. Again, bubbling up to the level of decision makers, and possible leadership positions you might find yourself in the future. If there are, if missing people or missing decisions who are about to default, for example, people who are about to default on a loan, which is the use case here. If missing them is costly, then accuracy alone will be misleading. Okay, so if you're always going to assume that people are not going to default, and some of them end up actually defaulting, then giving them loans is going to be very costly for you. This carries a cost associated with it, and it's a cost that you have to factor into your decision about whether or not you're going to deploy a model or not. There might be different costs associated with each of these two scenarios. So indeed, we might care more about the recall for the will default group. You want to catch as many will default people as possible, and ask yourself if that's the case or not for these two models. If the baselines give you a floor, so here the floor that we've found is 53.9. That's the worst possible accuracy we can find given this super simple baseline. If we have this baseline being a floor, then is that really what we'd expect, or does the decision context tell you what is expected? This is an important nuance to maybe get right also. A baseline tells you if you're getting any worse than this, then your model is this failing in an important fundamental way in terms of modeling, in terms of the data science and the statistics. But the decision context is something else. The decision context weighs in the other factors in the real world, like the ones we were just talking about, like the costs of missing people who are going to default beforehand. So somebody who wants to actually deploy this model that we've been talking about in this whole example would be not satisfied with 53.9% accuracy or with like 0% recall, obviously. So they'd have different levels of performance that they would deem to be necessary for deployment that would probably be higher or at least different than the baseline that you're dealing with. Which is another reason why it's always good to have a very difficult baseline to beat. If you're beating a baseline that is more stringent or more difficult, then whatever the use case demands, then you're going above and beyond your expectation, and that's always a good thing. Another worked example. So here's a little leakage trap to exemplify this issue. We'll start with the same lone default data set, but we're going to add this suspicious feature called label copy. So this is a really like pathologically simple example. It's rarely this obvious in real life, but sometimes it's close. But here we have an exact copy of the true label, and we're going to just basically put that into the input. So we're going to have like our risk score and the copy of the label we're predicting as inputs X, and we're going to predict the same label as Y, and we're going to see how performance changes. There's not too much going on here, so we're going to copy our original training set. We're going to take our prediction Y, and we're going to just add that column, that label we're trying to predict, to a new column called label copy in our leaky version of X. And then everything else is more or less the same. Actually, some things are different. We're going to do our train test split. We're going to stratify on our predictions as before. Now we're going to use our same predictions, but we're going to use the leaky data that has this extra column added to it. So we're going to have new sets here for X train leaky, X test leaky, Y train leaky, Y test leaky. Now we're using a far better classifier than the baseline we saw previously. We haven't seen logistic regression either. We're going to see that later on in this class, I promise. Here's another classifier that you can treat as a black box. Logistic regression will tweak its internal settings. That is to say, it's going to optimize its internal parameters in a systematic, step-by-step way, in an iterative way, and it iteratively improves its internal settings a number of times, and we can just say don't go more than 1,000 steps. This will make more sense to you in the future when you've seen this associated module. Anyway, but the logistic regression is a classifier, so sklearn. This is another function in sklearn. Implements the fit function. It's given training data as input. Once this model is trained, then we can make predictions on our test set. And again, our test set includes the label. The label's leaked into our test set here, and we can make our predictions. Once again, we get our accuracy scores, and we report it. I also, actually, I didn't show you, but I just also printed out the confusion matrix like we did before. We get 100% accuracy on the leaky test set. And here's our confusion matrix. This is like the ideal confusion matrix from some point of view. All 97 examples of class 0 are classified as class 0. All 83 examples of class 1 are classified as class 1. It's 100% performance. This sounds great. Sometimes you see 100% performance occurring realistically in the wild. A lot of the time, in my experience, that I've seen people reporting 100% performance, usually there's something bad going on behind the scenes that they haven't caught yet. So I guess you've already guessed what's happened. The model has the feature that is the answer key. Again, it's like writing an exam on a test set, on a test, but you know all of the answers in advance to every single question. So of course you're going to do well on the test. Even if you technically trained, again, you can look at the code very carefully, and training occurred on the training set only, but the training set, so there's no overlap of test and training, but the answers to all of the test set questions were given, at exam time to the model. So in production, you're not going to know if, again, realistically, you're not going to know whether the customer defaulted or not. So it's a ridiculous thing to have in the first case. But this just exemplifies that problem we previously were talking about. I would advise you just to, maybe have somewhat more realistic versions of this. Do not have an exact copy of the label, but you can take label Y and you can add a little bit of noise to it. When I say noise, I don't mean just adding a small number to it. You're going to have to, again, this is a class, this is a binary variable, but you can randomly flip some of the elements in your in your label copy to be different. So maybe only 90% of your label copy columns are exactly the same as your label. 80%, 90%, you can figure out what that is, but do the experiment and see what happens. You'll get a little bit less perfect. You get more imperfect performance, but generally you'll still get like unrealistically high performance on your held out test set. Sorry, I failed to scroll this slide. Can I show you it this way? No. Actually, yes, I can. Anyway, so the leakage in preprocessing, this is another subtle problem. So even without this obvious label copy problem that we just had in the previous example, you can still leak information in more subtle ways that is a bit more common. This is another example that I warned you about previously. Here we have our standard scaler. This is the z-score scaling we talked about in a previous module. We say we're going to use it, and then we take all of our data and we fit the transform on all of the data X using that scaler, producing a scaled version of all of the data. And then after that, we do the train test split and we get our, like on the scaled X, and then we get our training test versions of X and Y, right? The problem here is that we've previously scaled all of the data first, and then afterwards we split the data into training and test. So the scale is based on information that exists in the test set that we would never have had, beforehand during training. So the scaler has seen the entire data set, including the rows. See, I'm just going to bring it over here for a second, just so I can see the bottom here. So the scaler has seen the entire data set, including the test rows. We know this. The better way to do things here is to do the train test split first, and then after that's done, then you're going to say, I'm going to use the standard scaler. And at that point, after I've already done the splitting, I will fit my transform of my scaler on only the training set. That's a good thing. And I'll scale my training data. And then after that, I'll just scale the test set, but I won't fit and then transform the test set. I will use whatever the fit was on my training set. That is to say, the mu and the sigma I've obtained from the train set, and I'll just shift things over on my test set without relearning mu and sigma, getting my scaled test set. My test data scaled in proportions according to just the training set only. It's better to use a pipeline for this, which coincidentally is exactly what we're going to do now. You can learn about pipeline through this link, but it's an important, relatively powerful, or at least a good habit to get into. So here, the pipeline basically says, well, we're going to split the data first before we do anything. Then we're going to have this pipeline. A pipeline is going to be a sequence of steps. The first thing we're going to do is apply the scaler, and then we're going to do the logistic regression, or whatever the model is. And then you're going to fit afterwards, and then you're going to do the prediction afterwards. So pipeline is basically just a way of concatenating together a couple of steps so that you're not accidentally going to put them in the wrong order, or accidentally put things in between them. And to make sure you run through the pipeline from start to finish as well. So the benefits of using this pipeline is that all the pre-processing steps, here being the standard scaler, are going to be tied to the model and the training. So the pipeline automatically ensures this split. You can use a pipeline within cross-validation, and this also guarantees that if you're doing multiple folds, then all of these transforms, the standard scalars, are going to be applied to the training portion only, and it won't leak any information from the test sets or from the folds you're using as test sets. And it's basically, using pipelines make it harder to reuse information from the test folds generally. Again, there's lots of problems. You can use pipelines, they're not a silver bullet, but using them is good practice for doing machine learning, at least with the sklearn. For what it's worth, fancier machine learning libraries like Hugging Face also implements their own version of pipelines. So in summary, when you're looking at a model performance and you're applying it to a particular decision, it's always good to have a baseline. Your metric, whatever the performance is on your fancy model, needs to at least be better than these very simple baselines. Usually you want to find better baselines than the ones I'm talking about here, but we're just introducing this idea, so it's fine. Check the splits, so ensure that the split is appropriate. Ensure that if if there's some information of time, make sure that you're splitting based on time appropriately. So make sure that information from the future that you wouldn't have if you're making a decision at a particular point in time hasn't infiltrated the train test split. Make sure you're doing stratification for imbalanced classes. We talked about that previously. So just applying stratify equals whatever the variable you want to stratify according to as an attribute to your train test split is something you should be doing. Ensure that any pre-processing steps you're running are done using only the train portion, and you're not falling into the trap we saw a moment ago that the pre-processing of, like, say, scaling like leaks some information from the test set. Test your metrics, so ensure that they match the decisions that you're trying to make, and for imbalance problems especially when you're dealing with classifiers that are as simple as like majority class classification, be very suspicious of high accuracy. Again, a naive person, like an amateur, might look at a super high performance and get extremely excited and happy and think of themselves as genius machine learning people, but for you, when you see something that's like too good to be true, it often is. So that should be a red flag for you to go back and reinvestigate. Look at confusion matrices, look at the distribution of your data, and make sure that nothing sketchy is going on. Similarly, if both training and testing are very high and there's very little gap between the performance you get on the evaluation on the training set and the test set, this can be a little bit suspicious. Normally we expect to see a little bit of a difference between these scores. You ought to be able to do a lot better on training than testing because you have access to training while you're optimizing your model. And then again, going back to previous complaints, make sure that any features that obviously contain future information or are potential proxies or highly correlate with the things you're trying to predict, these features are bad. Try to identify them and remove them if you can. Over-promising impact is an ethical risk. Avoid, running to your stakeholders and showing off how performant your model is. It's always a good idea to go back and evaluate and reevaluate your results so you don't end up overemphasizing the quality of your performance, and also potentially targeting the wrong people. Like if your classification is entirely imbalanced and discriminates against groups of potential users, that would obviously be a bad thing. If there's leakage, if there's any kind of shortcuts occurring and the performance you're measuring is faulty in some way, then this can again, just generally like disadvantage some groups, but I think the bigger point here, not the bigger point, another point here is that like the resources you're applying to this problem and to this deployment end up being wasteful and harmful, and you're spending money or you're spending resources in order to deploy a faulty model. That's obviously a waste of your effort. And invariably, once your stakeholders, either your boss, your colleagues, the general public, your clients who are deploying a model that you've produced, or the users of your tool come to you and complain that, hey, this model that you said gets 83% accuracy, only gets 79% accuracy, like you lied to us, that's a huge problem. Even if technically you did not like outright lie to them, like they'll behave as if you did, so it's a lot better to put out models that are well evaluated and their ranges of performance are well documented so that you don't become embarrassed by that kind of scenario in the future. There are all kinds of mitigations you can take. Some of them include strong baselines. So don't just say how fancy you are, also include baselines that are a lot stronger than the ones we saw today. And say, well, so put your performance in context. Usually you do this with multiple metrics, not just accuracy, but accuracy and recall and precision and so on. Usually do this on multiple data sets, maybe even on multiple samples of the same data set. Maybe use multiple versions of the same model, so with like large transformer networks, which is going to be the subject of machine learning classes in your future. You're going to have small versions, medium versions, big versions, experiment with different architectures. You're going to have a ton of results that you're going to show people eventually. And then document a lot. A lot of people don't want to do documentation. They see this as sort of like a bit of an overhead that you have to do and you don't really want to do, but it's important because documentations can sometimes surface problems of the proxies we were talking about before. They can surface problems of time-related information or process-related information leaking in ways that are kind of avoidable and undesirable. And generally, you might, while you're documenting all of these comparisons, you might find that there are simpler, more transparent or understandable models that are still going to be baselines, but are, not as complicated as black boxes with suspiciously high scores that cost a lot of resources to deploy. So that'll be something that you'd end up observing through like deeper experimentation. So these simple ideas that we talked about today occur everywhere in data science and machine learning. So Kaggle competitions is among them. Oops, I'll just go back here, but you can follow up this link on your own. Kaggle competitions are basically provide these leaderboards in which these teams compete with each other. And then because you have these leaderboards with examples of other groups and other models performing very well on particular tasks, as long as the code is available and the models are available, which they often should be, then you'll have much stronger baselines than majority class classifiers. And often the data sets have been designed in a way to avoid, not all, but many of the kinds of leaks we were talking about today. And Kaggle competitions are still a way that individuals that are making a name for themselves can. You can also find good baselines in academic and industry papers. So some papers are retracted. So I still think going to conferences like ACL or NeurIPS, and like from those proceedings, all the papers are published. They're open and freely available. Code is usually available also, and the data sets they use are freely available. So you ought to be able to grab cutting edge models and do experiments on your own and see if you can make any tweaks that can make improvements. I just wanted to highlight, that despite the fact that, the vast majority of these papers are done with good intentions, even when they're done with good intentions, occasionally there are accidents that occur. So this paper you can follow up on identifies instances of leaking, and some papers have to be retracted because they realize only after the paper is published that, oh no, these results that we're reporting were suspiciously high, or they're the numbers we ended up reporting because we ended up leaking information from the test set, or there's device artifacts, like the imaging model was very performant because it was learning something about the devices that were being used at the different hospitals, and it was not really detecting cancer, it was detecting the hospital. And it was, and then that resulted in priors that affected performance. And then, does this beat our current rule-based system? I should have reworded this. I was thinking of rewording this. Rule-based systems are becoming increasingly rare now. But before you deploy a model, is there some status quo that is already being deployed? Is any new model actually going to beat it? Is always a question you're going to ask, whether it's rule-based or not. And whatever that baseline is, it could be existing human processes, which still exist. It could be a simple decision tree, something fixed and rigid and deterministic and constructed by hand. Or is it something more complicated? You're always going to have to answer that question. Here's some quick checks for you to run on your own, and feel free to talk to me about your solutions. Here's one and only reference we had today. Please check it out. As always, thanks for watching. See you next time.